Welcome back to Rock the JVM in 2021, folks. I'm Daniel, and this will be the first video of the year 2021, and I'm going to discuss about functors in functional programming. Now, as always, I'm going to write Scala in this video, but this concept will apply to other typed languages as well. For example, TypeScript or Java or C++ or any other typed languages that you are familiar with. So for this video, I'm going to assume some familiarity with lists and options as mappable containers, and I'm going to demonstrate what this means in the video. Now, as a recommendation, as always, I'll recommend that you code alongside me, and when you need to refresh your memory about functors, just refer back to this video or to the blog article at blog.rockthejvm.com. All right, so that being said, let's get back to the code. So in this project, I'm using Scala 3, but this concept is applicable to Scala 2 as well. And in the previous videos of Rock the JVM, I've already shown you how you can create a Scala 3 project. You can do File, New Project in IntelliJ IDEA, and in the wizard that pops up, you will select Scala and Dotty Experimental here on the right. And after you hit on Next, you can simply follow the rest of the wizard. It should be really straightforward as long as you have IntelliJ IDEA, and I'm using the version 2020.2, which is pretty recent and has some Dotty Experimental support. All right, so let's get back to this video and to the code that I'm about to write. This video will be pretty general because although we will write Scala, this article will focus more on the concept than on some very specific APIs. Now, this is one of the lessons of the CATS course of Rock the JVM, which we look at in general terms in this video. So in the CATS course, which I'm going to leave a link in the video, we talk about functors in much more detail with some exercises and whatnot. All right, now let's get back to functors. So pure functional programming deals with immutable values. So if you want to transform a data structure, we will need to create another one, not modify the old data structure. So you're probably familiar with the famous map method on lists. So I'm going to define a value. Let's call this an incremented list as list123, and assuming that I want to transform this list and increment each element by 1, I would say map, and to the map function I would pass a lambda that, given an int, you transform it to something else. So given an x, I'm going to return x plus 1. So this will be the list 234, and this will be a completely new data structure. But I already assume that you know this already. The thing is that this map transformation concept can be applied to other data structures as well, and Scala programmers are all too familiar with the concept of options, which are data structures which may contain 0 or 1 value. So if I define an option as option int, and on the right hand side I say sum2, this will be an option that contains 1 value. So you can think of an option as a list with 1 element. And I'm not going to explain why this is a useful data structure. We use options to validate and process values which may not exist so that we can circumvent defensive code with null checking. All right, so we use options as a solution to this problem. So these options may contain 0 or 1 value, and a try, which is a similar data structure which can wrap a desired value, or an exception if that computation fail. This is an equivalent or a similar data structure. So I'm going to define a try as try int with a capital T, and I'm going to say success with the value, let's say 42. And for this, I'm going to need to import scala-util try and scala-util success because these are not automatically imported. So try is a very similar data structure to option in the sense that it can wrap a desired value, or it can wrap an exception if that computation, if that expression fails. All right, and Java folks, by the way, they also use the optional type with the same semantics as Scala's option, and other type languages have very similar data structures in place. Now, the thing is that the map transformation that you saw here on lists is also applicable to options, tries, and other data structures as well. We've covered some of those in the monads video, which I really recommend you watch on the YouTube channel, and I'm going to probably dive deeper into those in another video. So if I want to transform this option, I would say a transformed option as an option map x arrow x times 10, for example. And this will be another option instance which contains the value 20 instead of 2. And similarly, a transformed try would be a try.map x arrow x times 10. And this will be a success with 420 wrapped inside. So this map concept is applicable to lists and to other kinds of containers like this. And to generalize this concept, I'm going to introduce the concept of functors. So for purely practical reasons, let's consider a very simple example that wants to transform a list, an option, and a try by multiplying its inside value with 10. So I'm going to define 3 methods. Let's call this do10x list, which takes a list of integers as argument and returns another list of integers. And I'm going to say list map underscore times 10, which is the same as list.map and with this kind of lambda, x arrow x times 10. And I'm going to multiplicate this method, so I'm going to duplicate this, and I'm going to make it applicable to options and tries, because that's the best that we can do right now. So I'm going to say do 10x option with an option as option int, and this will return another option int, and I'm going to say option map and underscore times 10 as well. And I'm going to copy that, and I'm going to say do 10x try, and I'm going to use try int this time around, and I'm going to simply say a try and a try map underscore times 10. So notice that we have duplicated code here because there's nothing better than we can do. If you want to support another kind of data structure in your API, you would have to define yet another method that would do basically the exact same thing, because if you look at the implementation of these methods, they are basically identical. It's the argument .map, and then you pass on that function. However, there's no need to repeat ourselves, because we've established that this map concept is so-called transferable. So we can create an interface for it. And in Scala, a transferable concept can be very easily expressed as a type class. And we also have a video on type classes in the Rock the JVM channel as well. So we will name this concept a functor, and I'm going to define a trait for it. So I'm going to define a trait functor, and this will be a generic in another type argument which is itself generic. So I'm going to say functor c underscore, where c will stand for a type which is itself generic, for example list or option or try. So this functor thing will contain a method called map, but this map will look a little bit different than the map that you normally see in the standard library. So you will need to supply some type arguments A and B, which are the concrete types of the container that you initially have and the container that you want to obtain. So the first argument will be a container, which will be a C of A, for example, a list of int, for example, and a function, which transforms an A to a B. And then at the end of the function, you will obtain a container with that type B. So this is the functor trait. So the definition is pretty compact, but I think you will be able to read it. So in order to use this map concept on various data structures, we will need to create implementations of this functor trait for various data structures that we'd like to support. So for example, on lists, we would have the following. I'm going to define a given value, and obviously we have a video on givens on the Rock the JVM channel. I'm going to link it in the description if you are interested in seeing that for Scala 3. So I'm going to use the Scala 3 syntax. So I'm going to say given list functor as functor list. All right, so notice that functor takes as type argument the list type itself, which may itself be generic. So I'm going to use the list type just as it is. And I'm going to need to override the map method. So I'm going to say def map. And the IDE is smart enough to suggest an implementation, a function signature for me. So override def map with the exact signature that I wrote in the trait. And as implementation, I'm just going to use the map method that the container initially has. because the list already has a map method. So I'm going to say container.mapf. All right, so this functor is an instance of functor for list where the map method just applies the standard library's map method on the initial container. Now, why is this useful? Why do we want to simply reuse the standard library map in another map function? Well, the interesting thing is that once we have functor instances for all the data structures that we'd like to support, for example, list and option and try, or whatever other data structures you might want to support, you can generalize this API. So instead of having 3 methods and needing to add a new method every single time you want to support a new data structure, instead, what you can have is a stable API, which is general enough. So I'm going to define def, let's call this do 10x, and I'm going to simply keep it at that, so do 10x, but I'm going to add a type argument, and this will be a higher kind of type C, which can be list, option, try, or whatever else you might want to support. And I'm going to use the container, which is, instead of a list int, is going to be a C of int, but I'm going to assume the presence of a functor for this kind of container in scope so that we can use it in the map. So I'm going to say using functor as functor of that container type C. And I'm going to obtain a C of int where the implementation is going to be, instead of container map underscore times 10, I'm going to use the functor. So I'm going to say functor map with the initial container and the underscore times 10 function that I used to use on this other multiplicated API. So this will be the duplicated API, and this is the one function stable API. Now, why is this useful? Why is this valuable? This kind of code is valuable because we've reduced this API to a single method, and we can now use it on different data structures provided we have a given functor in scope. So for example, this call do 10x with the list 1, 2, 3 simply works just as it is. So instead of me needing to do 10x list with list 1, 2, 3, where the presence of this API method would require me to support list, instead of doing that, I can simply call the general API do 10x with the container list 1, 2, 3, provided I have a functor list in scope. So the functor list will be implicitly passed by the compiler here, list functor. So this would be injected by the compiler automatically, all right? But I would have to comment that because the compiler doesn't like the second argument being passed explicitly as this structure over here. I would have to use using for the compiler to accept it. So notice that the compiler can automatically inject list functor just as it is because I've defined it as a given instance. So far this do 10x does exactly as this duplicated API used to do, given we have the functors for list, option, and try in scope. But these are easy examples because all of them already support a map method. This API is even more powerful because we can also choose to support data structures that does not have the map method inherently supported. And so I'm going to define a very quick binary tree kind of data structure, and I'm going to show you how this API can also be used to support this new data structure just by defining a functor in scope. So I'm going to define a trait tree, and I'm going to make it covariant. And I'm going to create 2 case classes. So case class leaf of plus t, and this will wrap a value of type t, and this extends tree of t. So this tree data structure will either be leaf nodes, which will wrap simple values, or they can be binary branches. So I'm going to define case class branch of plus t, and this will be a value. This will contain a value of type t and a left node, which is of type tree t, and a right node, which is of type tree t, and this extends tree t. Now, just to make this super compact, I'm also going to define some factory methods in a companion object. So I'm going to say object tree, and I'm going to define a method called leaf which takes an argument t and wraps a value. And this will return a tree t. This is very, very important. You need to define the return type of these factoring methods as the general trait type. And in the implementation, you can either choose to provide a leaf or a branch. So I'm going to say leaf value. And I'm going to define another method called branch, which takes a type argument t and then 3 constructor arguments. I'm going to pass these exact things as they are. I'm going to make this branch method return a tree t. This is also very important. So we specify the general interface. And I'm going to say branch with value left and right. So we've defined a very small data structure which denotes a binary tree. This can either be a leaf node or a branch node. And I'm going to show you how this stable API can simply support this new data structure just by adding another functor for this data structure in scope. So this is exactly what I'm going to do. I'm going to define a functor for this tree. So I'm going to define it as a given instance as well. So I'm going to say given tree functor, we scroll down so you can see better, as functor tree. And this functor tree will only need to support this map function that the functor trait will need to define. So I'm going to define map, and IntelliJ will suggest a method definition. And the map function will take a container as a tree of A and a function from A to B, and this will return a tree of B. Now I'm going to simply use pattern matching here. So I'm going to say container match. And in case we have a leaf wrapping a value, then I'm going to return another leaf node. So I'm going to say leaf with f of value. So this will be a leaf of B this time around. And in case I have a branch with a value left and right, I'm going to simply apply the function f to this value, and then I'm going to recursively apply map on this left and right subtrees over here. So I'm going to say branch with f of value, and on the left-hand side, I'm going to use map with left and f, and map with right and f. All right, so we simply recursively call map on the left and right subtrees over here. Cool. So let me show you how this do10x stable API can suddenly support a tree data structure. So I'm going to define a val tree, and I'm going to say tree.branch, and I'm going to say 1. This is the root node, and the left node is going to be tree branch with the node 2, and then let me use 2 leaf nodes. So I'm going to say leaf 3 or tree.leaf 3 and tree.leaf 4. All right, so this whole tree is the left subtree of the root node 1, and the right subtree, let me just use leaf 5 or tree.leaf. All right, so we have 1 as the root node. On the left hand side, we have yet another subtree with 2, 3, 4, and on the right subtree of the root node 1, we have a simple leaf 5. Cool, let's process this tree. So I'm going to simply say do10x on this tree. And notice that this stable API can suddenly support this tree because we've defined a given instance of functor tree in scope, and so the compiler can inject that automatically for us. And so because I've created this whole file here as an object, I can define a main method inside. So I'm going to say main and then type enter, and then I'm going to simply print line this new value over here. So I'm going to cut it out and print line inside. So let me go ahead and run this, and you'll notice that we obtain a tree whose values are processed in the exact same way while keeping the same structure. So we have 10, 20, 30, 40, and 50. So now it is the time where we should stand back and notice the power of a functor. It allows us to generalize an API and process any kind of mappable data structure in a uniform way without needing to repeat ourselves. So given a functor in scope, we basically assume that this container C is mappable in some way. And through the definition or through the implementation of a functor for that type, we have just made that type mappable, just like a list, just like an option, like a try, and many other data structures. So this was an example of how your stable API using a functor can suddenly support a completely new data structure without needing to modify the original API. All right, so I hope this is valuable. Now I'm going to go one step further, because with Scala 3's extension methods, or with implicit classes in Scala 2, we can attach the map method, the natural map method, to a data structure that normally does not have it. So I'm going to define an extension method. So I'm going to say extension. This is a new kind of structure in Scala 3. And for an extension method, I need to supply all the type arguments in advance. So I need to supply the type argument C, which is itself generic, the type argument A, which is the type of the initial container, and the type B of the resulting container. So I need to supply all the 3 type arguments in advance. And I'm going to wrap a container as a C of A. So given a C of A, this C of A will suddenly have a map method that I'm going to define later using a functor as functor C. So extension for the container C of A, given a functor C in scope, I'm going to define a map method that, given a function from A to B that you pass as argument, I'm going to simply call functor map with container and that function. Now, this structure is pretty compact. So what this means is that if you have the type C of A, then this type C of A, for example, a tree of int, this can suddenly have a map method if you have a functor in scope, where if you call the map method on this container, the implementation of this map method would be the functor that you use as a given value, functor.map, with that initial container and the function f that you pass inside. So I'm pretty sure this is still very abstract. So I'm going to simply show you how this extension method would work on this tree. So I'm going to define another value called 10x tree. And I'm going to simply say tree.map. So tree is a tree of int. And because we have a functor of tree in scope, the Scala compiler can naturally attach this map method, which takes a single argument, a function from A to B. So I'm going to say underscore times 10. And what the compiler rewrites that to is functor of that tree, which is tree functor, map with that initial container, which is the tree, and the function underscore times 10. So this is what the compiler rewrites this expression to, but normally you wouldn't see this. So this would be simply transparent to you as if the tree data structure was mappable just like a list. So this is the power of an extension method using a given instance of functor. So I'm going to leave this for your reference. So notice how you can make a new data structure mappable with a new functor. And obviously, if I print this out, so if I print line 10x tree, I'm going to see the exact same result. So if I right click and run this, I'm going to see the exact same process tree here in the output. So notice how a functor can extend the original API of your data structures. So functors are a pretty powerful concept in functional programming. I hope this video was valuable. If you did like this video, go ahead and give it a thumbs up and subscribe to the channel for more videos like this, and follow me on Twitter and LinkedIn for fresh updates on upcoming material. And check out the blog for the written version of this video, and check out the Rock the JVM website and the CATS course for more content like this. In the meantime, I'm Daniel, signing off.